Okay, imagine for a second how your own brain pulls up a memory. It's not really like searching for a file name on a computer, is it?
No, not at all.
You get a prompt, maybe a scent, a word, even just a feeling, and your brain activates patterns that are related. It's associative.
Hmm.
Sometimes you get exactly what you wanted, sometimes something similar, and sometimes, well, honestly, it feels like a totally unrelated jumble.
Right, that associative process where maybe a partial or noisy cue retrieves a whole pattern, that's just fundamental to how biological memory seems to work.
Yeah.
And it's a concept AI researchers have, well, long tried to replicate, especially now as models are grappling with these truly enormous amounts of data. How do you efficiently access the right information from just vast stored knowledge?
Exactly. And that brings us right to the core of today's deep dive. We're tackling a pretty dense, but I think fascinating research paper. It dives into modern Hopfield models. These are a type of associative memory model that have recently shown, well, incredible promise in deep learning, especially their ability to handle massive memory sets.
Yeah, our source material is this specific paper, and it's quite academic. It really delves into the theoretical underpinnings and um, the practical implications of these newer models.
So our mission today is to unpack this. We want to guide you through the paper's key academic contributions, the real innovations here. We'll try to translate the technical details into concepts that make sense.
Right.
We're going to focus on the novel ideas presented and really try to understand why they represent a significant step forward in this field.
Yeah, highlighting the conceptual shifts and the theoretical breakthroughs this work introduces.
Yeah.
That's the goal.
Okay, so let's set the stage first. Hopfield models, they aren't a brand new idea, are they?
No, no, not at all. The concept goes way back to the early 1980s. You had work by people like Amari and Hopfield himself, of course.
Right.
The classical models were heavily inspired by neural networks in the brain. They sort of envisioned storing memory patterns as stable states. Think of them like energy minima in a landscape, like valleys.
Yeah.
So you give it a query, and the system would dynamically evolve, kind of like a ball rolling downhill, until it settled into the nearest stable state, ideally one of the stored memories.
So the memory was the valley the ball rolled into. Got it. But these early ones had limitations, right?
Precisely. Yeah. Classical Hopfield models, they suffered from relatively low memory capacity. They just couldn't store that many patterns reliably. And their retrieval process could be slow, often requiring multiple steps, multiple updates.
Okay.
But then fast forward to 2020, and you have the introduction of modern Hopfield models, particularly the work by Ramsauer and colleagues. And this dramatically changed the landscape.
Okay, and what did these modern versions bring to the table that made them so exciting for current AI? What was the big deal?
Well, they brought several really key advancements. First, an exponential increase in memory capacity. They could store vastly, vastly more patterns.
Exponential, wow.
Second, incredibly fast retrieval, often just one-step retrieval based on a query. Huge speed up. And third, and this is crucial, they demonstrated really strong compatibility with deep learning architectures.
Right, and that compatibility wasn't just like a coincidence. I remember seeing the strong connections being drawn between these modern Hopfield models and the attention mechanism, the thing that powers transformer models.
That connection is absolutely significant. Yeah, it's pretty well established now in the literature. The mathematical structure, the actual calculations involved in the retrieval dynamics of modern Hopfield models have been shown to be deeply related to what happens in attention layers.
Interesting.
So this means modern Hopfield models aren't just some abstract memory concept. They can potentially serve as powerful alternatives or maybe enhancements to attention within neural networks. That's a major area of ongoing research.
Okay, so if they already had exponential capacity, one-step retrieval, deep learning compatibility, what fundamental problem or, gap was this specific paper trying to address? What was missing?
That's a great question. So while the standard or dense modern Hopfield model was theoretically very powerful, actually implementing it with truly massive memory sets was still computationally expensive. The complexity scaled quadratically with the memory dimension, which can be a bottleneck. Also, there wasn't really a single unified theoretical framework that could easily derive different types of modern Hopfield models and provide strong guarantees across all of them.
Okay.
So this paper really tackled both of those issues head on, the efficiency and the unified theory.
Right, okay, and here's where the paper introduces what seems like a genuinely novel theoretical perspective. This feels like one of its most significant academic contributions. Traditionally, these models were derived from thinking about an energy function, right? Trying to find dynamics that minimize some energy.
That's the classic approach, yes. You define an energy landscape where your memories are the low points, the minima. And then the dynamics, the rules for updating, are designed to move towards those minima.
Okay.
But this paper takes a fundamentally different view. Instead of starting with an energy function, they propose viewing the creation of the retrieval dynamics, the process that maps a query input to a relevant stored memory. They view that creation process as a learning problem itself.
A learning problem.
Yeah.
So you have your set of memories, and those are like your data points, your examples.
Exactly.
And you want to learn a function, let's call it t, such that if you give it a query x, which might be a noisy version of a memory or something just similar, it maps that query towards the closest actual stored memory, say celer. And this paper says, okay, let's use principles from machine learning to directly learn that mapping function t. Is that the core idea?
That's precisely it. They frame this learning task using concepts from support vector regression, or SVR.
SVR. Okay, for listeners maybe less familiar, can you give us a simple gist of SVR?
Sure. Think of SVR like fitting a line or maybe a curve to a set of data points, but crucially, with some tolerance and flexibility.
Yeah.
Instead of insisting the line passes exactly through every single point, SVR aims to find a function that lies within a certain margin, like a tube, around the data points. And it penalizes points that fall outside that margin.
Got it.
So the paper leverages this idea. They define the retrieval dynamics, this function t, as the function you get by solving a specific SVR problem. You're essentially learning a function that maps queries to their associated memories while trying to stay within a defined error tolerance, that margin.
And they refer to this framework as nonparametric. What's the significance of that label? They highlight it in remark 3.4.
Right. So nonparametric models in machine learning are models that don't assume a fixed structure for the function they're learning up front. Their complexity, how intricate they can get, can grow and adapt based on the amount or the complexity of the data itself. In this case, it depends on the number and structure of the memory patterns. This flexibility is an important academic insight, really. It allows the framework to potentially handle more complex memory distributions without needing you to manually redefine the model structure every time. It adapts.
So the big theoretical result here is theorem 3.1. It basically states that solving the specific SVR problem gives you the definition of the retrieval dynamics T.
Yes, that's the foundational mathematical result. It formally links this SVR learning framework directly to the memory retrieval process.
Okay.
And the real power of this perspective, academically speaking, is its unifying nature. By choosing different kernel functions, that's in the math, which essentially determine how you measure similarity between memories, perhaps in a very high-dimensional space.
Right.
By choosing different kernels, this single SVR framework can derive a whole family of different modern Hopfield models.
Wow, that's really elegant. So you just swap out the kernel function and out pops a different type of modern Hopfield model.
Exactly. If you look at Appendix E of the paper, they show how they can recover models corresponding to linear kernels, multi-head kernels, random feature approaches, and others, all derived from this one unified SVR perspective.
That's powerful.
It really demonstrates the academic strength of the new framework. It provides this common theoretical ground for understanding and generating different variants, which wasn't really there before.
Okay, so as a crucial sort of validation step, what's the first model they derive using this new framework? Did they check it against known results?
Yes,
Yeah.
absolutely crucial. They show in Lemma 3.1 that their nonparametric SVR approach successfully recovers the standard, dense, modern Hopfield model, the one introduced by Ramsauer et al.
Okay, the established one.
Exactly. And this is a vital sanity check. It shows that their new framework is capable of producing established results, which helps validate its correctness before they move on to new things.
Okay, the framework is validated. It works for the known stuff. What's the next major innovation they introduce using this validated framework?
This is where they directly address those practical limitations. We talked about the computational cost and potential noise vulnerability of the dense model. Theorem 3.2 introduces the sparse-structured modern Hopfield models.
Sparse-structured. Okay, does that mean what it sounds like? They aren't performing computations over all the stored memories simultaneously anymore?
Precisely. That's the core idea. Instead of calculating the relationship between the query and every single one of these, say, M memory patterns stored.
Which is what the dense model effectively does.
Right, which gets expensive if M is huge.
Right.
The sparse model incorporates a mask. It's formally defined in definition 3.3. And this mask restricts the retrieval calculation to only a specific subset of memories. Let's say a subset of size k, where k is much, much smaller than the total number of memories m.
So the idea is to kind of intelligently select just a few relevant memories to interact with the query rather than engaging with all of them, including potentially irrelevant ones.
Exactly that. Theorem 3.2 shows how their nonparametric SVR framework, when you apply it with this masking concept incorporated into the learning objective, naturally yields a sparse retrieval dynamics, T-sparse. This is a really key academic result, deriving this sparsity directly from their principled SVR learning perspective.
Okay, and the practical payoff of achieving this sparsity?
Well, the big payoff is that this sparse structure allows for the development of truly efficient variants, models with sub-quadratic computational complexity. That's highlighted in remark 3.6.
Which is a huge improvement over the quadratic scaling of the standard dense model.
A massive improvement, especially crucial for handling very long sequences in NLP, or just huge memory sets in general within deep learning. It really fills a significant gap for making these things practical at scale.
And do they connect this sparse idea to other methods?
Yes. They show how this general sparse concept connects to more specific, practical ideas like using random masks or window-based masks, which relates to efficient attention mechanisms like Big Bird and Longformer.
Ah, interesting connection.
And also top K selection, where you just pick the K most similar memories based on some initial check.
Yeah.
But it's important to note, and the experiments show this later, the way the sparsity is implemented really matters for achieving actual practical efficiency gains. Just saying sparse isn't enough.
Right, the implementation detail is key. Okay, so we have this powerful new theoretical framework. We have derivations of both the standard dense model and these novel sparse models from it, but theory needs solid backing. What are the key theoretical guarantees they provide specifically for these new sparse models? This sounds like the academic heart of it.
It really is. Section 4 is packed with the core theoretical contributions for the sparse models, providing robust analysis. A primary result is the retrieval error bound they derive in Theorem 4.1.
Okay, and what makes this error bound particularly interesting from an academic standpoint?
The crucial finding, the novel part, is that the upper bound they derive on the retrieval error, basically, how accurately the system retrieves the target memory, is shown to explicitly depend on the sparsity level. Specifically, it depends on the size of that support set, K. And they show that a smaller K, meaning more sparsity, leads to a tighter theoretical bound on the error. As remark 4.1 points out, this explicit dependence on sparsity in the error analysis is a new contribution compared to prior work on dense models.
Wait, that seems almost counterintuitive. Using less information, a smaller subset K could lead to potentially more accurate retrieval, theoretically.
It suggests that by focusing only on the most relevant memories, the ones in the small set K, and effectively filtering out potentially irrelevant or noisy distractors from the larger set M, the system can actually achieve more accurate retrieval.
Ah, filtering out the noise.
Exactly. And this ties directly into noise robustness, which they discuss in remark 4.2. The sparse models are theoretically shown to be more robust to noise, either in the query itself or within the stored memories. Because the term in the error bound that relates to the impact of noise has a smaller coefficient, thanks to that sparsity factor, K. Essentially, less noise gets propagated through the system because you're interacting with fewer patterns.
Okay, that makes sense. Better theoretical accuracy bounds, better noise robustness.
Yeah.
What about the speed of retrieval or convergence? Does sparsity help there too?
Yes, corollary 4.1.1 suggests that the tighter error bound derived for the sparse dynamics implies they might require fewer iterations, fewer update steps to converge to a stable fixed point compared to the dense dynamics. So potentially faster convergence.
Okay.
And importantly, they maintain that prized property we mentioned earlier for modern models. Corollary 4.1.2 shows that, provided the memories are sufficiently well separated, the sparse model can still achieve accurate retrieval in just one step.
Which is vital for using them like a layer in a deep network.
Absolutely. That one-step retrieval is key for seamless integration.
And you mentioned fixed points. Did they prove convergence without relying on that old energy function concept? That sounds like a significant theoretical departure.
Yes, absolutely. And this is another really important theoretical point made in the paper. Corollary 4.1.3 proves that these retrieval dynamics converge to fixed points, but, and this is the key, without appealing to or needing to minimize an energy function.
How did they prove it then?
The convergence is established solely based on the properties derived from the SVR construction framework itself. Decoupling the convergence proof from the traditional energy function perspective is, I think, a novel and important theoretical path for understanding these associative memory models.
Okay, fascinating. Finally, the big one, memory capacity. That exponential capacity is a hallmark of modern Hopfield models. Do the sparse versions somehow lose that advantage?
No, they actually argue the opposite. Lemma 4.1 and Proposition 4.1 discuss the condition needed for successful storage and retrieval, which involves memories being sufficiently well separated from each other.
Right, they need to be distinct enough.
Exactly. And they demonstrate theoretically that sparsity using a smaller k actually makes this well separation condition easier to satisfy.
How? Because you only need the memories within the sparse subset K to be well separated from each other, rather than requiring all M memories across the entire set to be distinct from every other one.
Precisely. You've relaxed the constraint. It only needs to hold locally within the active subset. And this implies, as they note in Remark 4.4, that the sparse models can potentially store an even larger number of patterns than the dense models, while still maintaining that desirable exponential scaling property of capacity.
Wow. So you get the efficiency benefits and potentially even better capacity scaling.
That's the theoretical argument, yes. Better efficiency without sacrificing and maybe even enhancing that massive memory capacity.
This is a really compelling theoretical package they've put together. Does the experimental evidence actually, bear this out in practice? Did they run tests?
Briefly, yes. They did include experiments, presented in Appendix G, which provide empirical support for these theoretical claims. They aren't the main focus of the paper, which is heavily theoretical, but they're important.
Okay, can you give me maybe a couple of standout examples from the experiments?
Sure. One good example is the multiple instance learning, or MIL, task. You can see this in figures 3 and 4.
What's MIL about?
It involves analyzing bags, or sets of instances, where many of the instances within a bag can be irrelevant noise or distractors. You need to find the key instance.
Okay.
And the results show the dense model struggles significantly as the number of instances in the bag, the potential memory patterns, increases. It gets overwhelmed trying to process everything.
Right.
In contrast, the sparse models, specifically ones they label sparse Hopfield and top K variants, maintain high accuracy even with these large bag sizes.
So they handle the noise better.
Exactly. It strongly supports the theoretical claims about noise robustness and the ability of the sparse model to selectively focus on the relevant patterns and ignore the distractors. The training curves also generally showed faster, more stable convergence for the sparse and also the random feature models they tested.
Okay, that supports the accuracy and robustness claims.
Hmm.
What about demonstrating that promised computational efficiency? Was it actually faster?
Yes, figures 6 and 7 are key for that. They show the computational efficiency results, looking at runtime and FLOP's floating point operations, and the truly efficient variants, specifically the window, linear, and random feature Hopfield models, the ones designed with efficient sparse implementations in mind.
Right, where the implementation matters.
Exactly. They demonstrate a clear and significant reduction in runtime and FLOPs as the memory size scales up compared to the standard dense model. So this empirically validates that sub-quadratic complexity analysis. It's also worth noting, looking at those figures, that while the general concept of a sparse or top K mask reduces the theoretical number of memories considered, the practical efficiency gains really came from those specific structures like window or random feature. The naive sparse or top K implementations didn't always show the same speed up in their tests, likely due to implementation overheads in standard libraries at the time.
Got it. So the theoretical sparsity needs careful implementation to become practically fast. Okay, so let's try to recap the major academic contributions here. This paper provides a powerful, new, non-parametric theoretical framework.
Yes, fundamentally rooted in support vector regression.
Which shifts the perspective away from energy minimization towards seeing retrieval dynamics as a principled learning problem.
Exactly, a really fresh theoretical angle.
And using this framework, they not only recover existing models, like the dense one, which validates it, but they also formally derive these novel, efficient, sparse variants.
Right, variants that then come equipped with strong theoretical guarantees established rigorously within the paper.
Guarantees covering things like better retrieval accuracy bounds that depend explicitly on sparsity.
Increased robustness to noise, potentially faster convergence, the ability to maintain that crucial exponential memory capacity, possibly even enhance it by relaxing the separation requirements.
All while proving convergence without needing an energy function.
Correct. A whole suite of theoretical backing for these new sparse models.
Which is, well, a really big deal for making these powerful memory mechanisms truly practical for the massive scale we see in modern deep learning.
Exactly right. These theoretical and practical advancements, particularly the unified framework and the efficient sparse models, are paving the way for building AI systems that can handle larger, more complex data sets. Think improved efficiency, better robustness, maybe faster training or inference.
Across all sorts of applications, presumably.
Yeah, from analyzing huge images or videos to processing very long time series, maybe complex genomic data. It's about providing a solid, novel theoretical foundation for these incredibly useful memory tools in AI.
It really feels like this paper managed to provide both a fresh theoretical lens and address some very concrete practical bottlenecks at the same time.
I think that's fair to say.
Yeah.
That reframing, moving from the traditional energy-centric view to this learning regression framework derived from SVR, combined with the rigorous derivation and analysis of the sparse models, really represents a significant academic leap in the field of associative memory, especially its connection to deep learning.
Okay, so let's leave you, the listener, with a thought to consider, perhaps drawing from some of the paper's own acknowledged limitations or future directions. The paper does note that strictly guaranteeing convergence to the exact target memory, the perfect retrieval, can sometimes depend on specific kernel choices. And also, the theoretical analysis for the sparse models sometimes assumes the correct memory is actually present within that selected sparse set K.
Right, those are fair points about the currents.
So how might future research maybe bridge these gaps? How can we ensure these theoretical benefits, the accuracy, the robustness, hold up reliably even with messier, more correlated real-world data, where memories might not be perfectly separated, or where a simple masking approach might occasionally miss the ideal target memory in that initial selection?
That's a key direction, yeah. Improving robustness and selection in more complex scenarios.
Or thinking about that connection to attention mechanisms again. Given that this paper showed how different kernel choices derived from this SVR framework connect to various known attention mechanisms, what entirely new forms of attention or maybe completely different memory mechanisms could this unique non-parametric SVR-based perspective unlock next? What haven't we even imagined yet that might stem from this new way of thinking about memory retrieval as a learning problem?